The purpose of this video is to prove the theorem that non-degenerate eigenfunctions of Hermitian operators are orthogonal. So if we start off with an eigenvalue equation, and this time we're going to be a little bit more specific, that we're going to refer to an eigenvalue equation that's true for one particular state of a system. And so here we mean specifically that when A operates on psi n, where n is some particular value of a quantum number for that particular quantum system, that returns an eigenvalue a sub n that's particular for that quantum number n, and of course returns the wave function psi n back again. We also want to define an eigenvalue equation for another state of the same system. So again, if you want to think about this in a concrete way, this could be a particle in a box problem where we're simply defining the eigenvalue equation for different values of n equals 1, and then the eigenvalue equation for the n equals 2 state of the particle in a box, if you want to think about a concrete case of this. So obviously we have then two eigenvalue equations. I'm going to call those equations 1 and 2 just for easier reference, because we're going to manipulate these equations algebraically. The first thing I want to do is take eigenvalue equation 1, and I want to multiply that entire equation by the complex conjugate of the function for the state m, the one I referred to in the second equation, and I want to integrate that equation as well. And so if I go ahead and do that, left-hand side is simply plugging in the complex conjugate of psi m on the left-hand side, integrating that over all space, and then doing the same thing on the right-hand side. That's the first two terms here. And what we can do to the integral on the right-hand side is we can pull the eigenvalue a sub n out in front of the integral because it's a scalar value, and that just leaves behind psi m star psi n integrated over all space. If I now work with my second eigenvalue equation, and I take the complex conjugate of this equation, which means I can distribute the complex conjugate operation through all of the terms in the equations like we did in the previous video. And then if I go ahead and multiply by psi n, the wave function from the equation 1 eigenvalue equation, and integrate that over all space, on the left-hand side I have basically the result of doing this to the left-hand side of my complex conjugate equation. That is equal to doing the same thing to the right-hand side, where I take psi n times am star times psi m star integrated over all space. Like I did before, I can pull the scalar value am star out in front of the integral. And I can further, just to make life easier in the next step, is I can switch the order of psi n and psi m star in that integral. We talked about this in the previous video as well. Multiplication is associative. It doesn't matter what order I multiply the functions. And that leaves me with the new equation 4, where am star is out in front of the integral, and then the integral itself is psi m star times psi n integrated over all space. So here are my two new equations that I've generated. Equation 4, I just generated. Equation 3, I generated from eigenvalue equation 1. If I subtract equation 4 from equation 3, on the left-hand side of that equation will just be the difference of the two integrals from equations 4 and equations 3, and then the right-hand side of the new equation will be, of course, the difference of the right-hand sides of these two particular equations. What I can do is look at the left-hand side of the equation first, and I can see that the left-hand side of the equation has to be equal to 0. And the reason for this is the Hermitian property itself of the A operator. If you recall, the first integral that I have listed here, that is equal to the second integral I have listed here. So if I take the difference in those two integrals, then automatically that has to be equal to 0. So the left-hand side is equal to 0 because of the Hermitian property of the A operator. And then the right-hand side, what I can do is, because I have a common integral now, I can group the two eigenvalue terms together, and so I have an minus am star times the integral psi m star psi n. If my actual wave functions psi n and psi m are not degenerate, meaning that they are not the same wave function with the same energies, then that means their eigenvalues are different. And so an is not equal to am by definition. And so that term in front of my integral, that can't be equal to 0 by the way I've defined things. Because we're non-degenerate, because the eigenvalues are defined as being different, then that of course requires that the integral on the right hand side, that has to be equal to 0 to satisfy this particular equation. And so what it means when we have an integral that's equal to 0 for two functions, it means those two functions are orthogonal. And so geometrically this means the two functions are at right angles to each other. What that means more practically to us, however, and what we're going to take advantage of in the future, is that when we see integrals of functions that we know are non-degenerate, that we know those functions, the integral of those two functions, that will be automatically equal to 0. Just like what we know when we have the integral of two functions that are identical and we bother to normalize them, that integral is equal to 1. And so here we know this integral is equal to 0. And we'll be able to take advantage of this property in the future. We'll generate some nasty looking integrals in some cases, but in many cases we'll say, well, we can see that those two functions are orthogonal to each other, and that integral is going to be 0 by definition.